let's learn what is the intuition behind A/B testing. So A/B testing is what you do when you want to find out causality. You want to say that, hey, this thing caused this thing, right? So for example, let's say you are having a website and you want to be sure that, let's say, button that looks black in color with the black text is better in terms of people clicking than a button with green in color with green text below it. It's a very simplistic example, but there are already two components here that I'm testing at the same time. I'm testing black button with black text, two things, green button, green text, two things. If I want to test which of these two things are working better for my website, like which one will give me a higher number of people clicking it, and eventually they'll buy more of my goods because they're clicking the buttons on my website. So the way you find out and be sure that this button is better or that button is better is you run an A/B test. What do you do with that? You get lots and lots of people and you divide them into two buckets. Let's say we have 120,000 people. We take the first bucket, 60,000 people that are visiting your website, and put them in this experiment, which is the version A. So this is version A of your product, and this is version B of your product. So you're basically having two versions of your product, version A, version B, and you're trying to find out A or B, which one is better, and by how much. Let's say, so then you look at, okay, if I have 120,000 people coming to my website every day, I can divide them into two buckets. One bucket, which is version that goes to version A, will have 60,000 people, and another bucket, equal size, 60,000 people, will go to version B. Yeah. So you can start to see that, hey, you're dividing your site traffic into two, and then finding out who is clicking and what is, let's say, the statistic that you use here is average click-through rate for these people. Let's say you find out that 60,000 people that were in this bucket were clicking this button at the rate of 8% average CTR, meaning the first person in that bucket was clicking, they're coming to the website, but they're clicking it 7% of the time, that click-through rate. Second person had 9%, third person had 2%, 16%, and so on and so forth. So you have click-through rate for each of this person in this 60,000 bucket people that you have. So the average click-through rate of all of these numbers, let's assume, is 8%. So you have a bucket with an average percentage that you have for that bucket. Similarly, you have this other 60,000 people who you assign to this treatment. You find out what are those click-through rates for all of them, and so then you find out, oh, their click-through rate is 2%. The question now is, can you conclude that given that this bucket of users, almost 50-50, yeah, had 8% CTR, this bucket had 2% mean CTR or average CTR, and the difference between them is 6%. Yeah. So how do we know whether this 6% that you observed with this running this experiment one time is significant? Because can we say that this is just by chance, that this button was not really that good to drive an incremental 6% lift? It's quite possible that you run this experiment tomorrow and then you get these numbers reversed. You get 8% here and 2% here. Yeah? So it's quite possible. So the difference that we are observing here between these two buckets, how do we know whether this is a causal effect here, or is this just by chance that you see a 6% difference? So that's where we can use A/B testing, not just by assigning them different buckets, running them once, finding out that, hey, I have an hypothesis. You create a hypothesis and say, hey, my null hypothesis is that there is no difference, and that this 6% difference that we are seeing is purely by chance. That would be my null hypothesis. And so what you do is you now look at these two data points that you got right? 120,000 data points, one bucket here, the other bucket here. And what you do is you scramble this, meaning you change the 7% was assigned to 1. What if this 7% was assigned here to this user 60,004? So you scramble the percentages and then you get randomized output. You get randomized output. Basically, you are moving the CTRs randomly across these buckets, and you see that, hey, this 1%, this first user is now having a CTR of 1%. And so that 1% came from, let's say, this user was assigned here. And then user 2 now no longer still has, let's say, randomly 9% because it was assigned some other 9% user here. User 3 got 1.5% instead of 2, which is basically you reassigning this 1.5 CTR here. Similarly, these bucket users in green will now have CTRs assigned from any random bucket. It could be from the black bucket or it could be from the green bucket. So you see that we have randomized and assigned random CTRs to these users. So when we do this once, we get a scramble. We get a randomization effect. And what we then get is the CTR here. So let's imagine this CTR was 6%. And this CTR after one randomization was 3%. So the difference now you observe with this randomization is 3%. So what you do is you get this 3% difference between these two, and you get one data point here. Yeah, you get one data point here. Yeah, so similarly, we did this one-time randomization. We can do this a million times. Scramble this data randomly million times. And so what you will get is a distribution like this, where there will be more and more people around the mean, yeah, and then less and less on the extreme. So you will get differences that will look like this. So once you get a million such randomized assignments, you will see more and more of them will be centered around the mean and less on the extreme, meaning the differences between these two will reduce over time. And so then what you look at is, if my confidence threshold is like, hey, I am confident if my threshold is, let's say, 95%, meaning I want the difference to be such that it is only for top 5% of the users. Meaning, if my 6% difference that I got, yeah, is only observed less than 5% of the time, yeah, that's your p-value. So you find out the p-value for the 6% difference that you have, and let's say we find out the p-value for the difference that's of observing 6%, which is, let's say, somewhere here, and we find out that, hey, this p-value is 0.01. That means there's only a 1% chance that you can observe a difference of 6% that you observe here. What that means is that it is not by chance that you observe this. There's a very low chance of observing a data point like this. So anything that is less than 5%, when your confidence is 95%, anything less than 5% would be significant. So when your p-value is less than 5, because your confidence is 95%, you want anything above 95%, then anything less than 5% is significant. So in this case, you got p-value of 0.01. That means this is significant, meaning you cannot ignore the fact that this is just by chance. This is significant. What that also means is that this is evidence against the null hypothesis. When you have p-value of, let's say, 1%, which is less than 5%, meaning you can say that, hey, this is not just by chance. So you can reject the null hypothesis. So when you get p-value less than 0.05, that's evidence against the null hypothesis. You reject the null hypothesis and you say, hey, no, null hypothesis said there is no difference and it's purely by chance. So you say, no, this is not by chance because my threshold is 5% and confidence 95%, then I would say that this is significant, meaning there is indeed a difference between um, this button with this text CTR, and this green button with this CTR. Yeah, so that's the intuition. Basically, you try to find out how rare is the possibility. If it's very rare, less than 5% chance that you get an observation with this kind of a difference, and your confidence is 95%, then you say, hey, there is indeed a difference. But you could also increase this confidence to 99%, meaning you only will agree if your p-value is less than 1%. So then this significance is not significant anymore for you. It has to be like less than, it has to be 0.001 or something like that, much smaller than 0.01 for you to find it significant. Meaning you're only looking for this extreme values, these extreme cutoff values. Initially it was like, hey, anything here I would count as significant. Yeah, so 0.25 here and 0.25 here, I counted as significant. So that's the intuition behind A/B testing, where you try to find out, hey, is this by chance? And then you look at millions such randomized samples, and to find out how rare is the possibility of observing what you observe for your given test statistic. Yeah, so that's the intuition behind A/B test. How you find out what is the p-value for your observed difference from a million such possibilities, and then you could do 10 million. Yeah, and then you find out, hey, this is indeed significant, so you reject the null hypothesis. When you reject the null hypothesis, you say, hey, there is indeed significance, and this is much better in terms of click-through rate, and there is indeed a difference between these two buttons. Yeah, so that's the intuition behind A/B testing. Thanks.